and the recording is rolling. So this is the second lecture, as I said. And what we did last time, the final thing we did was that we looked at how components of a vector field change in curvilinear coordinates on Euclidean space. Now, so this is something that we can look at in a more general space as well. So let me start by looking at derivatives in more general spaces. So the problem with curvilinear coordinates was that our vector basis was not constant. It depended from point to point, which meant that in order to find how a vector field changes, we could not just look at the change of the components. Instead, we had to look at something like this. So we had change nabla A acting on VB, where V is a vector field. This was given by the partial derivatives of the components, but we also had to add this term. Let's see, yeah, BVC, right? So this term with the Christoffel symbols. So these gammas were called the Christoffel symbols. Now, in a general space, such as a sphere, let's draw a sphere here. So there is no technology is not with me today. So on the sphere, if you look at one point, for example, if we look at this point, tangent vectors to the sphere are going to be in the tangent plane here, this point. So this tangent plane might look something like this. Now, this is not necessarily the same as the tangent space over here. So a priori, these tangent spaces are completely different spaces, and we can't really compare vectors at one point to vectors at the other point. So the question is how we're going to define derivatives. And the answer to that is that there is some freedom in how we define those derivatives. And that freedom is exactly what appears in these gammas here. So in general, a directional derivative on a general space is defined through this relation up here. So exactly with what I wrote. And these gammas, this Christoffel symbols, or more generally connection coefficients, they define what we mean for something to change from point to point. So in general, there are going to be several possible directional derivatives, and these gammas are going to define what we mean when we say a directional derivative. In the case of Euclidean space, we define that through the fact that we had Euclidean space and we can identify the tangent spaces at different points to each other. And then there's a natural way of relating them to each other. But in a general space such as the sphere here, this tangent space a priori has nothing to do with that tangent space. So we have to be a bit more careful. And there are actually several different ways that we can do this. For example, on the sphere, we could say that, well, vectors don't change if they are pointing in the same bearing, so to say. So a vector at this point pointing north, and at a different point pointing north, we could say that they are pointing in the same direction. And that's one possibility of saying that things don't change. Another possibility to say that things don't change is to say that if you take a geodesic line, so essentially the shortest path between 2 points, then a vector does not change along that line if it keeps the same angle and the same length to sorry, it keeps the same angle to that line, and it has the same length. So there are different ways of defining this on a general space. So this brings us to the concept of straight lines. What do we mean when we say a straight line? So what would you say that a straight line is in Euclidean space?
The shortest path between 2 points.
That is one way of defining it. Can you think of any other definition of a straight line? We're going to come back to that definition in a while.
No, I can't think of one right now.
So if you look at the tangent vector of a straight line, so if I draw a straight line here, let me draw a straight line. Oops, well, fairly straight. If I look at the tangent vector here at this point, and I look at the tangent vector at this point, what can you tell me about the relation between those two?
The slope of the line is constant.
Yeah, the slope of the line is constant, or equivalently, this tangent vector here, if I call it k, is the same as the tangent vector k over there.
Right.
So they're pointing in the same direction. So this is the alternative definition of a straight line that I'm going to look at the beginning, and then we'll come back to the definition in terms of the shortest path. So once we have a derivative such as the one that we just defined, we can define a straight line is a curve with constant tangent. And this constant is going to depend on of course, the derivative that we have defined in the space. So in principle, if I have a curve gamma, so if I make a more general curve here, and the parameter t, and we call this curve gamma, we denoted the tangent vector of this curve by gamma dot. Then this line is straight if the directional derivative of gamma of the tangent vector gamma dot in the direction of gamma dot is equal to 0. So this is called the geodesic equation. So it means that with this definition of what a derivative means up here, if the derivative of gamma dot here is 0 along the curve, then we have a straight line or geodesic. And what this geodesic is of course going to be dependent on how we have defined this derivative. Also note here I'm using this notation that if I write a vector in the argument instead of an index, and I act on a different vector y, this is given by xa nabla a acting on y, and the components here of this is that. Okay, so that's what a straight line means. So if you write this out, so we know that, so this is going to be called the geodesic equations.
Excuse me?
Yeah.
What is a geodesic?
A geodesic is a curve that satisfies this condition.
Okay, thank you.
So a curve whose tangent is constant along the curve, essentially. It doesn't change along the curve. There is a different definition that we'll come back to in metric spaces, which is exactly what was said before, that the geodesic is, in those cases, is also the shortest path between two lines. And we're going to see that they coincide. So if I write these geodesic equations in component form, so the components of of this tangent vector gamma dot. That's the time derivatives of the coordinates. So I can write this geodesic equations as follows. And this should be equal to 0. Now, if I write out using this definition of the derivative, if I write this out, what I get is chi dot A dA acting on chi dot B plus chi dot A gamma ACB chi dot C. And I'm going to leave the second term here, I'm going to leave as it is. But the first term, let's look at what this actually is. So here we have gamma dot chi dot A d chi A. But this is just d chi A dt times d chi A, which according to the chain rule is just d dt. So if we use that, this is chi double dot B, so the second time derivative of the coordinate, plus, and I'm just going to rearrange the terms a little bit here. So I put the gamma first, chi dot A, chi dot B, and this should be equal to 0. So this here is the coordinate form of the geodesic equations. And we should remember this form for later. So if you have a curve given by these coordinate functions of this curve parameter t, if those coordinate functions satisfy this equation, then the curve is a geodesic. Any questions on that?
I have a question regarding is the thing the line you wrote here, does it apply? Is it defined as a straight line according to this one?
This line?
Straight. No, the drawing you made.
This line? Or this one?
No,
the second one.
Yes.
So that depends on what I have defined as this derivative.
Okay.
I could probably, I mean, in Euclidean space, no, that is not a straight line. But if I have some other space where I have some other definition of what it means to change from point to point, it might be.
Okay. Thank you.
So let's come to exactly what you said for straight lines from the beginning. So let's discuss curve lengths. So if I have a curve, let's take a curve gamma, parameterized by t, and I can then ask the question, what's the length of this curve? How are we going to compute the length of this curve?
Did you ask us? Or?
Yes.
You take a small line segment and then you integrate over it.
Yeah, exactly. So
from one point.
If I take a point here and a point there, and I look at the small line segment there, it has a length ds, and the length I'm going to define as the integral of ds, well, from point A to B if I have to have particular endpoints. That's the length from A to B along the curve, right? So what's this ds? Well, if you look at the tangent vector here, well, let's call it dx. Dx is the small distance from the start of this line segment to the end of that line segment. And if I want to write dx in terms of the curve parameter, so this dx, that's dx dt times dt, right? Because it's just how the position changes with time multiplied by the change in time, or curve parameter. So how am I going to relate this to ds? In Euclidean space, all we do is that we square dx, right? So ds squared is equal to dx inner product with dx. That's just Pythagoras' theorem, essentially. So this means that what I have is that ds is the square root of dx times dx, or equivalently, the square root of the square of the tangent vector times dt. So if I want to write this in general coordinates, this square has to be written with a metric. So this is g of x dot square root and then dt. Or if I want to write this in coordinates, the square root of gab chi dot a chi dot b and the square root of that times dt. And then I make this integration, so I put the length is the integral from, well, if we have here t equals to 0 and here t equals to 1, then I would have the integral from 0 to 1 of this thing here. So square root of gab chi dot a chi dot b with respect to time. Okay, so I mean, just a quick example of that. So, oops, should turn off that. So, example, let's take the circumference of the circle, just to see that it works. So, well, you know what the circumference of a circle is. It's 2 pi times the radius. So in this case, let's take in polar coordinates r equal to r0, and phi then is a parameter. You can say that phi is the t parameter, and t here goes from 0 to 2 pi. So this means that if we look at the components of the metric here, grr is 1 and g phi is r squared, which on the circle is r0 squared. So this means that r dot is 0, phi dot is 1, which means that this expression here, gab chi dot a chi dot b, that's g phi dot squared, which is just r0 squared. So the length in this case is the integral from 0 to 2 pi, and then the square root of r0 squared is r0, and our curve parameter is dt, so we end up with 2 pi r0, just as we should, right? So the question becomes now, because you mentioned that that a straight line was also the shortest path between 2 points, right? So let's discuss the relations between that. So geodesic versus shortest path. So what we have now in general, so let's take these 2 points. Have A and B, and we ask what's the shortest path between those, and you know that in Euclidean space it's just this line. But in general, we can ask ourselves, what's the equation that these shortest paths should fulfill? Because in general, I can take many paths between those 2 points, and the way to do that is, of course, to take the expression for the length of a curve between A and B and minimize it. And so that's the length is a functional, and we minimize that function. So that's going to be variational calculus. So what we have is that the length here was this integral of this square root GAB chi dot A chi dot B dt. So I'm going to call this L, and the Euler-Lagrange equations are now going to tell us that the L, the chi A minus the dt, the L, the chi dot A should be equal to 0. And this should be true regardless of what A is. And if we perform this derivative, let's see what we get 1 over 2L, and then we get something as follows: chi dot A, chi dot B, dc times GAB minus d dt 2 chi dot A GAC. And I've exchanged A for C, so let's actually do that up here too. So I used C's here. And that's just because they were C's in my lecture notes. Okay, so I have now made one small assumption, and that's that the following. So that's that L is constant. And that just means that regardless of what curve I have, I can reparameterize it in such a way that the tangent vector has constant length. It's still going to have the same length, but it's just a reparameterization of the curve. So that has allowed me to pull L out of this time derivative, essentially.
I have a question.
Yeah.
Where did the C's come from in the expression?
No, so the C's are these C's.
Okay. Okay.
So I mean, I started by writing A's here, and then I changed them for C's because that's what I had in my lecture notes.
Okay. Oh, I see.
So,
Because C can be either
C can be any index, and
okay.
A and B are summation indices.
Right. Okay.
So if I multiply this by let's see, minus G dc times L, I mean, the right hand side is still going to be 0, and the left hand side is going to take a slightly different form. What I find is the following. Yes, I should say that this guy, the G with the indices upstairs, is defined as the inverse of the metric. So G dc GCA, for example, is delta dA. So if I multiply by that and perform the derivatives here, what I'm going to end up with is the following equation. So chi dot dot D plus chi dot A, chi dot B, that's what I already had in the equation, 1 over 2, and then I have dA GCB plus dB GAC minus dC GAB. Now I have taken this derivative of of the metric. I split it in two because the metric is symmetric, so I can do that, and that has become those two terms. But if you do this, this is what you will get, and this should be 0. Now, does this remind you of something that we have already talked about today?
Wasn't it the equation on the first page?
No, exactly. I mean, if we go back 2 pages maybe, here, it's exactly on this form, right? It's exactly on this form, just exchanging, that's actually wrong. I have put a B instead of a, oops. This guy should be a C. Otherwise the indices don't match up. So it's exactly on this form, right? Because we have, first we have this second derivative of the coordinates, then we have 2 first derivatives of the coordinates, and we have some gamma. So it's exactly on the same form as we have here. We have the second derivative of the coordinates, we have the first derivative of the coordinates, and then we have some other thing here where I have actually forgotten the inverse metric. So GDC. Otherwise the indices don't match up. So if we take now this thing here, this to be gamma D AB, then we have exactly the same expression as we had from the geodesic equation. So, so if this is the definition, of gamma DAB, then we recover the geodesic equations. So if we define our gammas to be this, then we have the exact correspondence to what we have in Euclidean space, that the shortest path between two lines is also the path along which the tangent vector does not change. So this is a very common way of defining how things change from one point to another, that we use those exact gammas, these Christoffel symbols, and then many of the properties that we had in Euclidean space follow over to more generalized spaces. So this expression for gamma, if I write it out again, so gamma A, B, D, typically written 1/2 GDC, and then DA, GCB, plus DB, GAC, minus DC, GAB. This is a nice expression. It's computable if you have the metric, but it's not very practical. Instead, if you really want to compute these Christoffel symbols, it's typically better if you do it exactly in the way we did when we derived this. So we use this variation calculus. Now, instead of using this expression that I had here, I'm going to use a different expression, which is the following. I'm going to define some S, which is 1/2. Instead of the square term, I'm going to have GAB chi.A chi.B dt. So this is essentially the same, except for the 1/2 in front and the missing square root. But it turns out that this is exactly the same expression. Well, it has the same solutions under this additional condition that the tangent vector is constant. So I'm going to use this to compute the Christoffel symbols. I'm going to do this in polar coordinates. So we already said that GRR was 1 and G5 phi was R squared, which means that this GAB, chi dot A, chi dot B, that's R dot squared plus R squared phi dot squared. And so our L is 1/2 times this. So if we look at the R coordinate, for example, we want to have that dl, the R, which is R phi dot squared, it should be equal to d dt, the L, the R dot, which is just R double dot. So this tells us that R double dot minus R phi dot squared is equal to 0. And if we identify this with the geodesic equation here, this means that gamma R phi phi is equal to minus R. It's this coefficient that's in front of the phi dot square. And we can do the corresponding thing for the phi components. Any questions on that?
Yeah, I have. Oh yeah, Hugo, go first.
Now just so this new definition of gamma, does it agree with the old definition?
Yes. So I mean, if you do this in Euclidean coordinates, in Euclidean space, everything agrees with what we did in Euclidean space.
Okay, so what's the difference in doing it in Euclidean space when you're calculating?
So I mean, in Euclidean space, you can go to different coordinates. Different coordinates might be good for different things, of course. But in a general space, we can't go back to these Cartesian coordinates that we knew from the beginning. The metric will have a structure that you cannot necessarily put it such that you have coordinates where the metric components is just the delta. I will come to an example of that in just a few minutes.
Okay.
I have a question.
Yeah.
Yeah, about the square root in the integral sign. Why did we skip it this time? I missed that.
So the thing is, if we look at this equation that I got here, the thing is, to get to this equation, I had to assume that L would be constant, so that I have to have reparametrized my curve in such a way that the tangent vector has constant length. I can always do that without changing the length, right?
Right.
So if you look at what's inside here, that is exactly the Euler-Lagrange equations that you would get if you instead would minimize this.
Okay.
So minimizing this is exactly equivalent to actually minimizing the length, but under the additional condition that the tangent has constant length. If we don't have that condition, of course, we have a multitude of solutions with different reparameterizations.
When you say that the tangent has constant length, do you mean that the tangent vector is like its absolute value is the same, but the direction changes?
Exactly. I mean, the direction does not change. That's the point.
Okay.
That's how we defined it. But in a general curve, yes, it changes. But for the geodesic,
oh right,
since
right.
you put it to 0, it doesn't change.
Yeah, right. Okay.
Yeah. Okay, so let's look at one case of a general space. Let's start first by looking at the general application to classical mechanics. So we're going to start coming into physics. So you know that in classical mechanics we have this Lagrange formulation. And so let's first define what configuration space is. So configuration space is if I have a physical system the configuration space is the set of possible configurations of that system. So the space of all possible configurations of a system. So, for example, let's take a double pendulum. So I take something that looks like that, and so this double pendulum now what's the configuration space? Well, it's all of the possible positions that this double pendulum might be in, and that is a two-dimensional space, and it's described by two coordinates. I can take them to be theta and phi. So this is a two-dimensional space. Is this Euclidean space?
Yes.
Is it? So with Euclidean space, if I start going in some direction, I never come back. If I have parallel lines, they are never going to converge and so on. But in this case, what happens if I let phi go to, say, what happens if the system, say, let's say that phi, this lower mass here, it goes around the full lap. Then I come back to the same position, right?
Right.
So if I have a single pendulum, that would essentially be given by a circle. So this is actually two circles. So the configuration space here is a torus essentially, because if theta goes from if I add 2 pi to theta, I come back to the same. If I add 2 pi to phi, I come back to the same system. But in general, for many physical systems, let's say with coordinates, I'm going to call them Q now because it's very common in physics to use Q for your coordinates. I used chi before, but let's call them Q in physics. So how can I express the kinetic energy? So for example, for this double pendulum, well, the masses are embedded in Euclidean space. That is true. So I can write down the kinetic energy in Euclidean space, but they depend on these coordinates. So in the end, I'm going to be able to write this kinetic energy in the following form: TAB Q dot A Q dot B. So it's of second order in the velocities, right? That's where these coordinate derivatives come from. Now, this TAB here is going to turn out that it has all of the properties that the metric has, and it's called the kinematic metric. So I typically also have some potential energy. That's just a function of configuration space. It's a function of just the coordinates. And what I do when I want to see how this system behaves is based on Hamilton's principle. I construct this action, and I put that the action should be equal to the integral of the Lagrangian with respect to time, which is defined then as this t minus v dt. So in the case of no potential, what does this action become? It's not a trick question. So if I remove that, then all I have left in the action is this kinetic term. So I have that S is 1/2 TAB Q dot A Q dot B dt. Now, this looks strikingly similar to what we just had here, right? So we had this, where this is exchanged for t, and well, the coordinates I just renamed them to q. So this is exactly the same expression, which means then that for this classical system, that the system evolves along the geodesics of this kinematic metric TAB, as long as there is no potential. If there's a potential, then we have an external force acting on the system, and so you do not move along these geodesics. But instead, the change in the geodesic, or the change from the geodesic, is going to be given by the external force. Any questions?
Yeah, I have a question about the. So, was the double pendulum non-Euclidean or Euclidean space?
It's non-Euclidean.
Okay.
I mean, it doesn't even have the same topology as Euclidean space, because here you have like two circles that you can go around and you come back. So if we draw the.
The idea is that when you travel along a straight line and you can reach the same point, that means it's non-Euclidean?
Yeah, well, I mean, it can also be non-Euclidean in many ways, but in particular here, we don't have an infinity.
Okay, yeah, you're right.
So, for example, if I draw this square in phi, so I have theta and phi space here. The points along this line are all the same points as along this line. And the points along this line are all the same as the points along this line. So if you think about it, it's going to have the same shape as a donut, essentially. So it's 11 o'clock. So let's take a break there. And we reconvene at 1:15. If you have questions, of course, I'm here throughout the break. Okay, so I hope everybody's back. It's 1:15, and let's continue. So in the break, I took the liberty of drawing another double pendulum, which I'm going to use as an example, just so that we can see how the kinematic metric and also the potential behaves in this situation. So in this case, if we write out the positions of both masses, so of mass 1 and of mass 2, and I'm going to write them relative to this point here, then x1 is equal to L1 times E1 sine theta minus E2 cosine theta. while x2 is going to be exactly the same. It's going to be x1 plus L2 E1 sine phi minus E2 sine phi. Now, the kinetic energy in this case is 1/2 m1, the time derivative of x1 squared, plus m2, and the time derivative of x2 squared. And if you take the time derivatives of both x1 here and of x2, and you square them, you're going to end up with the following expression. So it's going to be 1/2, then m1 plus m2, then L1 squared theta dot squared, plus we're going to have a cross term, which is 2m2 L1 L2 theta dot phi dot cosine phi minus theta. And then we're going to have one final term, which is m2 L2 squared phi dot squared. Now, this is exactly on the form that we discussed. This is equal to 1/2 TAB Q dot A Q dot B, where we can identify that T theta theta, that's just what's in front of the theta dot squared here. So that's M1 plus M2 times L1 squared. T phi phi, well, that's what's in front of the phi squared term. So that's M2 times L2 squared. And finally, we have T phi theta, which is equal to T theta phi, which is 1/2 of this term. So that's M2 L1 L2 times cosine phi minus theta. Any questions on that? In particular, people usually have some problems with the fact that this this corresponds to half of this, but that comes from the fact that in this expression you have two contributions, one from T phi theta and another from T theta phi. Okay, so let's continue. Let's take actually another example. Or rather, let's not take another example. Let's do the following instead. Let's check the case when we have a potential. So with a potential, we had the following expression. So we have the action, which is the integral of 1/2 TAB Q dot A Q dot B minus the potential of Q dt, right? Now I call this this T and I call this V. So if I write down the Euler-Lagrange equations for this, what I'm going to end up with is in essence the following. So I'm going to have dl dqa minus ddt dl dq dot a equal to 0. But if I split the Lagrangian into the kinetic part and the potential part, this tells me that dt dqa minus d dt dt dq dot a, this is equal to dv dqa, where I've just moved the potential term to the right. And the potential does not depend on the time derivatives of the coordinates. That's why I don't have this second term for the potential. Now, this thing here, the kinetic part, we computed that. That was the derivative that gave us the geodesics for this kinematic metric when we had no potential. And this is equal to minus TAB times, let's get it right, chi dot C, nabla C, chi dot B. And of course, in the case where I didn't have potential, this was equal to 0, which meant that this was equal to 0. So what I can do now is that I'm going to call this AB, and it's the acceleration. It's the double time derivative essentially of the tangent. And if I define this as this, then what I get is the following equation. It's AB equal to minus TBA DAV. And do you recognize this equation in some form?
Isn't it Newton's?
No, exactly. I mean, this is just a generalization of Newton's equation. For example, if we take the example of motion in just one dimension, then we would have t equal to 1/2 m x dot squared, and we would have some potential v of x. And what this would tell us is that, well, txx, the only component of this kinematic metric, is just m, which means that the inverse of that is 1/m. And then if we take this equation and write it down, well, it only has one component because it's just one-dimensional motion, and that's a, which is the second time derivative of x, which is equal to minus 1/m times dxv, which is the derivative of v. So this is the force, essentially. The force is minus the derivative of the potential. So this would be F/m, sorry. That's just Newton's equation. And if you go to things like where the coordinates are angles, what is going to be on the right-hand side here instead is torques. And on the left-hand side, you're going to have the angular acceleration instead. So this is a pretty neat summary of how these things work in general coordinates. Okay, any questions on that so far? If not, we're going to move on to what is called Noether's theorem. And this is possibly one of the most important theorems of classical theoretical physics. It's going to relate symmetries of a system to conserved quantities. That is to say that if you can see that your system has some sort of symmetry, then you're going to know that there is a conserved quantity, which means that you're going to be able to integrate the equations of motions. Examples of this is one example is that energy is conserved. We're going to see that corresponds to a symmetry under time translations, that the system looks the same, or rather that the problem looks the same if we translate it in time. If you take a solution to the system and you just translate it in time, it's going to be a new solution of the system. That's the symmetry part, and then that means that energy is going to be conserved. And this is called Noether's theorem after Emmy Noether, a mathematician. She lived in the beginning of the 20th century, and interestingly enough, she found that this theorem that is essentially central to modern theoretical physics, that was not such an important result. But she was proving wrong on that, I think. So let's consider the following. So let's say that we have a physical system of precisely the type that we just described, and we're going to see that we're going to assume that we have a continuous symmetry. So let's first define what this means. So let us consider a one parameter transformation. So a one parameter continuous transformation such that t goes to some new time, which is going to depend on t and a symmetry parameter s, so continuous symmetry. And at the same time, I'm going to send all of the coordinates to new coordinates qa, which are going to depend on the q and also on this symmetry parameter. For example, I just write the example here on the right, time translations. So translations in time. In this case, I would send t to tau, which is t plus s. That's a translation in time. And at the same time, I send qa to qa. So I don't do anything with q. But this is a continuous symmetry, translating a motion in time. Now, for small parameter values, I want that, well, one condition is going to be that since the symmetry is continuous, when I put s equal to 0, then tau is going to be equal to t, and small qa is going to be equal to big qa. So for small s, I can make an expansion of this. So I'm going to write that tau is equal to t plus s times some function delta t plus higher order terms in s. And qa is going to be qa plus epsilon times delta qa. Sorry, not epsilon, I used s here. Delta qa plus higher order terms in s. So here I'm going to restrict myself to delta t equals to 0 or 1. So either I have some time translation or I don't have any time translation. I mean, if I have a symmetry with some other delta t, I can always reparameterize s such that delta t is 0 or 1. And that's going to change the q, delta q. Delta q is going to be a general function of essentially both t and q. Okay, so let's then define what we mean by symmetry, or rather a quasi-symmetry. So a quasi-symmetry of the system with Lagrangian L is a transformation such that for this small parameterization, that S times delta L, which I define as the Lagrangian of Q, Q dot, and tau minus Lagrangian of the untransformed variables. This is equal to a total derivative of some function f. So this is the definition of a system, of a symmetry, sorry, that or a quasi-symmetry. That if the change in the Lagrangian when I make this transformation is a time derivative of some function, then it's a quasi-symmetry. If this time derivative is 0, then we call it a symmetry, because then the Lagrangian in the transformed variables is going to be the same as the Lagrangian of the untransformed variables. But all we're going to need is that it's a quasi-symmetry for Noether's theorem. So in general, if we look at this delta L here, I can express this delta L regardless of what Q is. I can express delta L as follows. It's dl the QA, so the derivative of the Lagrangian with respect to Q, times the change in Q, plus derivative of the Lagrangian with respect to Q dot times the change in Q dot. But the Lagrangian can also depend on time, so in general we're going to also have dl dt times delta t. Okay. So to clarify something that was not done properly during the lectures, let's take this expression that we had for delta L. And what I want to focus on now is this partial derivative of L with respect to time. So we can write the total derivative with respect to time of the Lagrangian as dl dqa times the derivative of Q with respect to time, so Q dot A, and the same thing for the next term, dl dq dot A Q dot A, plus the partial derivative of L with respect to time, where we have the partial derivative. So inserting now this expression up here, moving the other two terms to the other side, so move these two terms to that side, then we obtain over here the following, that we have dl dqa delta qa minus Q dot A delta t. For the second term we have dl dq dot A delta Q dot A minus Q double dot A delta t. And then finally we have plus dl dt, where we have, instead of the partial derivative of L with respect to t, we have the total derivative. Now, if we look at this expression, we should remember the following, that if we have an on-shell solution, that is a solution that solves the equations of motion, then that is going to satisfy that d dt dl dq dot A is equal to dl dqa. So if we take this expression and insert it here for for the derivative of L with respect to Q, this is going to mean that we end up with delta L equal to d dt acting on the L dq dot A delta QA minus Q dot A delta T plus dl dq dot A and multiplied by d dt of delta QA minus Q dot A delta T. Then plus this total derivative dl dt. Now if we look at those two terms and just apply the product rule for derivatives, this is d dt times dl dq dot A multiplied by delta QA minus Q dot A delta T plus the Lagrangian L. And we have just forgotten to write out some delta T's here. Let me just add them. And there is the final expression, which we used in the lecture. Yeah, anyway, so the point is, the end result that I'm going to get to is the following. If I have an on-shell solution, so this is true for any cube. But if I have an on-shell solution, so that means that if I have a solution that that satisfies the Euler Lagrange equations, then I'm going to be able to write this in the form d dt dl dq dot A delta QA minus Q dot A delta T plus L delta T. Now, this is a total derivative. And this means that it's going to be a total derivative for any on-shell solution. But according to our assumption, it was also equal to df dt for this function f, if we have this transformation that is a quasi-symmetry. Which means, of course, that both sides of this equation, both this guy and this guy, are total derivatives, which means that they can differ by at most a constant. So this means that that f, sorry, let's write it the other way around. If I take this dl dq dot A delta QA minus Q dot A delta T plus L delta T minus F, this is a constant, which we can call J. So if I have this quasi-symmetry of the Lagrangian, then I have this equation of motion. Or rather, not equation of motion. I have this constant of motion, sorry. So what does this mean? Well, so let's look at what we have actually. We have the following. Well, let's just look at this J again. So let's look at this constant of motion, which was F minus the L, and now I'm changing the sign here, but Q dot A delta QA. I'm rewriting it a little bit. The L, the Q dot A, Q dot A minus L delta T. I'm going to introduce a bit of nomenclature here. So I'm going to define PA as the derivative of L with respect to Q dot A. This is called the canonical momentum. With respect to the coordinate QA. And I'm also going to introduce what's going to be called H, which is PA Q dot A minus the Lagrangian, and this is called the Hamiltonian of the system. So this means that if I write G in terms of these, it's going to be F plus the Hamiltonian times delta T minus PA delta QA. And that's then the conserved quantity. Any questions?
Yeah, I have a question about the definition of the variation. So when you say little delta, what exactly do you mean?
So it's, if I take these functions, right? I take this transformation. That's a function of, well, of time and of the coordinates respectively.
Right.
And then I make the series expansion in S.
Okay.
And that's the linear term, which is then I mean, in general, here a function of the coordinates, and here a function of time, but I normalize it such that delta t is 0 or 1.
Okay.
So in the case of delta t is just 0 or 1, and in the case of q, it's a function of the coordinates.
Okay.
So I mean, let's take a few examples of this. So let's take kind of the simplest example that we can think about. Spelled like that in English. So a free moving particle. In 3 dimensions. So in this case, we have that L is 1/2 m x dot squared, right? So if we want to look at the change of this Lagrangian when we make transformations to x, so we get that delta L is m x dot times delta x dot. And we have that the canonical momentum P, well, that's the L dx dot, which is just your normal momentum, m times the velocity. We also have that the Hamiltonian is P times x dot minus L, which is just going to be m x dot squared over 2 again. So the Hamiltonian is equal to the Lagrangian one when we don't have a potential. So let's consider a few transformations of this, just to get a feeling. So the first one we can consider is let's consider delta x equals to constant as an example. So I can put this equal to x0. What does this mean? Well, it means that that essentially x goes to x plus s x0 because my delta x was x0, and that's what I'm putting in here. So it also means that the change in the time derivative of x is 0 because the derivative of a constant is 0. And because of that, we have delta L is equal to 0 because delta L depended on delta x dot. So this means that translations are a symmetry of the system. If you translate the system, you're going to get a system that looks just the same. That means that there's going to be some conserved quantity related to this. And that quantity is going to be this J that we talked about. And in this case, if we look at the definition here of J, well, F was 0 because the change in the Lagrangian was 0. Delta T was 0, so we don't need to care about that term. And we're going to be left with this term. And that term is going to be minus P times delta X. Which is exactly what we had here. And that's equal to minus P times x0. And since x0 was a constant, and in this case, it's an arbitrary constant. Any constant will be a symmetry of this Lagrangian. It means that regardless of what x0 is, this must be constant. And that means, of course, that P is a constant. So translational symmetry corresponds to conservation of momentum. A second symmetry of this system is if we put delta T equal to 1 and delta X equal to 0. Now, this does not change anything. It gives you delta L equal to 0 again. In this case, J, well, F would be 0 again. We would have the Hamiltonian times delta T, which is 1. And since delta X is 0, this is the conserved quantity. So this is constant. And it's just m x dot squared over 2, which is the energy of the system, which is going to be conserved. And we can take a non-trivial example. Let's take rotations. Now this system is going to be invariant under rotations as well. So rotations, for a rotation, we're going to have that delta X is going to be given by omega cross product with X, where omega is the axis of rotation. And if we put this, or rather if we compute delta X dot here, well, omega is constant, so we get omega cross X dot, and that means that delta L is m x dot inner product with omega cross X dot, which is 0 because X dot is orthogonal to anything, to any cross product of itself. So x dot here and the cross product including x dot, they are orthogonal, so this is equal to 0, which means that rotations are a symmetry. And if we check what we get out of that, we would get that j is equal to minus p. Again, delta t here is 0, so times delta x, which was omega cross x. I can rewrite this as omega, just by cyclic permutation, p cross x. And since omega here is constant but arbitrary, have rotational symmetries about all of the axes, this means that p cross x is constant. So this is conservation of angular momentum. Any questions on that? You're all silent because you're struck by the beautiful Noether's theorem.
Yeah, I'm on the last line where we rewrote the cross product. I'm a bit confused there.
No, it's just that I mean the cross product is anti-symmetric in all the arguments. Well, this triple product is anti-symmetric in all of the arguments. So all I did was change the position of p and omega, and I got the minus sign.
Okay. All right. I had a question. It's a couple of pages back.
How many?
One more, I think.
Yeah.
Yeah, exactly. So the equation in the middle of the page, where you have like S times
This
delta
guy.
L. Yeah, exactly. I'm just wondering, shouldn't that the expression between the the most left-hand side and the rightmost.
So the middle expression.
Yeah, exactly.
Yeah.
Shouldn't, like, intuitively, I'm thinking that is delta L, but maybe it's not.
I mean, depends on how you define delta L. I wanted delta L to be a finite quantity for small transformations, because this is written for small transformations. And in that case, I would have to include S all of the time in delta L, and I didn't want to do that.
Mm.
So that's why I have taken the S out.
Okay.
I mean, it's essentially the same thing as I'm saying here. Basically, what I'm saying is that that L of Q dot tau, that's L of Q dot T plus S delta L plus higher order terms.
Mm.
So in some sense, it's the same as these expressions.
Okay.
Just that delta L is then the what multiplies S in the linear terminus.
Mm.
Okay, we have 7 minutes. I don't really have time for another example, and we have gone through basically all of the theory that we wanted to. So unless there are any questions, let's finish here. And I'm going to stop the recording. If you have questions, of course, you can hang around later and ask them.